Today we're going to talk to you about how Azure and DataStax Enterprise powers the Office 365 per-user store. So I'm going to start by giving an introduction of who we are and what it is that our organizations do. And then we're going to talk about what we built and why we needed to build it. We're going to talk then about how we built it using Cassandra and Spark, and then why we chose Azure and DataStax Enterprise as the platform to build it on. Now, at that point, Silvano's going to step in, and he's going to talk about how you can build it on top of Azure using some good tools that were built. So my name is Sean Usher. I'm a senior software engineer in Office 365. Contact information is there. My team really focuses on currently running Cassandra for other teams in Office, as well as building platforms on top of Cassandra so that we can understand our customers better. And this is Silvano Coriani. He is a principal program manager in Azure, and he'll talk more about himself when he tells you how you can build it. So Office 365, I'm assuming many people here are familiar with it. You've probably heard of Word and Excel and Outlook, but those are client-level products. They're also server-level products. So historically, enterprises would buy things like Exchange for running email, SharePoint for document management. They would get the hardware, install it. They would maintain networking, machines, disks going bad. And Office 365, we take all that overhead and we move it into Microsoft managing it. So IT admins can focus on adding business value on top of that instead of dealing with what disks broke last night. And then Azure, which I hope all of you know of. It's Microsoft's cloud computing platform. It provides compute, database services, machine learning, mobile services. If any of you aren't familiar with Azure, come talk to Silvano after the talk, and please sign up for Azure trials so you can start deploying things and see how it works, and maybe even deploy Cassandra. So what did we build? So in Office 365, because we're hosting all these services for a lot of large organizations, and they all use services in different ways. Some people rely heavily on email, some people rely on SharePoint, and some people use features of those services more than others. So what we really need to understand to provide good service to them is how they're using it and what their experience is like. And historically, we've had synthetic monitoring that would run to try to simulate user experience. And we would have passive monitoring that would look at server logs and give us aggregated data on how users were experiencing the platform in different pieces of hardware. But then we couldn't say, you as an organization are having this experience in our system. So we really wanted to build a way to understand our users and their organizations at a deep level. And to start doing that, we wanted to answer, well, a few easy questions and a few really hard questions. So the first one is, are users happy with the service they're receiving? This is a really hard question because how do you come up with a number that says they're happy or not? And then are users fully utilizing the service they're paying for? You know, if we have an organization that's signed up for 1,000 licenses and they're using 500 licenses, we don't want them to have to pay that extra cost. We want to be able to reach out with them and work with them and give them a better experience. Are users hitting issues we can proactively help them with? Issues can happen on our side. They can also happen on the organization's side. They could go and make some licensing changes, and their users are still trying to use the service, but they're not getting access to it. And we need to be able to reach out to them and say, hey, we see that a problem happened that's impacting a lot of your users. How can we help you fix it? And what has a user's experience been over their lifetime? In order to provide good business value for a company, you have to be able to show them that you're providing business value. And one of the ways of doing that is to show them, hey, here's your availability, here are the number of support cases, here are the number of incidents you've been impacted by, so they can really go to their leadership and say, Office 365 is providing us with value. And then there's a really difficult one on how do we discover patterns in our data that we aren't aware of. Are users going to pages, following some kind of wizard and then leaving? Now, if we're seeing a lot of users doing that, that could mean that, well, maybe our page is broken, maybe it's not intuitive, and it's something that we need to feed that data back into the product to say, here's how we can provide a better experience. So to do all of this, we need to store a lot of data. But more importantly, we need to be able to aggregate on this data fast. If we take 24 hours to come up with this insight about the customer and discover their problem, they've probably already called support, they probably already fixed it, and we're going to come to them too late and say, hey, we knew you had a problem, eventually. So we had a few requirements. We wanted to run in the cloud. We manage bare metal in Microsoft and Office 365 all the time, but that adds an overhead if you want to dynamically scale. We also wanted to, of course, be highly scalable, ingest around 50,000 events per second to start with, rapidly growing. and a few other common requirements. The biggest one for us is really tunable consistency. We've used a lot of data services in the past that enforced full consistency. And when you're writing a lot of data and looking at aggregates of data, losing one piece of data is not really the end of the world, but having your whole pipeline backed up because you can't get full consistency means you can't do anything with the data, and then you can't tell your customers anything or help improve their experience. We also wanted to be able to do real-time and batch analytics, as well as machine learning. Machine learning can help us understand what we don't know about our data. And long-term storage. So we need a system that really can scale on the storage side of things. And one big requirement from management was it gets done in a month. So we started off not knowing what data system we wanted to use. So we started looking at some things that are public, some things that aren't public, but really what met all of our requirements: linear scalability, tunable consistency, running well in Azure, and had a big ecosystem around it so that we didn't take on a technology that we wouldn't have any support out there if something went wrong, was Cassandra. So we said, okay, let's take the bet. We know that some people in Azure were already partnered with DataStax and working on Cassandra, so we decided to try it. So we started deploying it. We went with one physical data center. Eventually we want to geo-replicate, but for now, one data center with two logical data centers, one for Cassandra and then one for analytics. So in order to deploy these, we decided to put them all in a VNet, assign static IPs, separate roles into different subnets, and then be able to ACL all the endpoints to the subnet so that we aren't exposing our backends to the internet where any zero-day flaw can then let someone come in and steal all of our data, which is pretty bad for us. So because we didn't understand how Cassandra would scale, we've never used it before, we said, let's go and get really big machines. So we went with 16 core machines, 224 gigs, 3 terabytes. And we decided we wanted to be able to set this up fast, so instead of building the integrations ourselves between Spark and Cassandra and configuring that, we would go and use the DataStax package, so we had to use Ubuntu. So here's just kind of a table of what we deployed. We have larger heaps in Spark because it ends up pulling in a lot of data from Cassandra at once to do aggregates. And G1 garbage collection, which when I get to the problem section, that was very big for us. It reduced our garbage collection times quite a bit, our pause times. And everything uses replication factor of 3 between our two logical data centers. So here's our ops center picture, just in case anyone cared. So we had to get data into Cassandra from Office 365. And I'm not going to say the number of servers we have, but it's a lot of servers in Office 365. And so to do this, we didn't want to have the servers directly talking to our Cassandra servers. We wanted to have a queue so that the clients didn't have to deal with retrying data that needed to be replayed or couldn't be written. So we decided we'd go with the REST API, and behind that API, we'd put a queue. But we chose the Azure Event Hub. So where a lot of people would choose Kafka, we didn't want to go and try a whole nother technology while we were learning Cassandra as a technology. Now, there are some people in our group who are looking at Kafka and trying to weigh the benefits of Kafka versus Event Hub. And Spark Streaming doesn't have an Event Hub receiver. So we created a set of Azure worker roles that use the DataStax C# driver, and they watch the queue, pull the data in, and ingest it all directly into Cassandra. And all data is ingested into the Cassandra data center, and then it's replicated to Spark, where our Spark jobs aggregate it. And all of our data is scrubbed for identifiable information. So if anyone did look at the data, they wouldn't be able to tie it back to any of our users or organizations. But Microsoft systems can tie it back. So for the next 2 slides, I wanted to show an example of our data model. 2 of our main entities are users and organizations. We also call organizations tenants. So our big ingested data is user dataset raw, which really is scaled by user ID and device because we know that users are going to get more devices over time. And we also have time PK in there. So what we didn't want to happen was a lot of events come from a device, creating a large partition, which can then cause compaction issues. So time PK has the day that the event was written. And if we see that a lot of events start happening from a device, we can change that to the hour that the event was written. And since only Spark reads this table, all we have to worry about is, do Spark jobs still run within the SLA that we have set when we have more partitions? And this is a time series piece of data. So our clustering key is created time. We do use date-tiered compaction strategy. And we'll talk a little bit about why we use date-tier compaction when I get to the problems. And our other main entity is really tenant, an organization. That might be hard to read, but what's important about this, the partition is tenant, and then we have a set of SKUs that you can sign up for in Office 365. So that is our clustering key. So one tenant can have multiple SKUs. Now this is not date time series. This gets bulk imported once a day, and then we import diffs as needed. And this really gives us metadata about an organization. Where are they? How many licenses do they have overall? How many licenses per system that they use, be it Exchange, SharePoint, Skype for Business? Are they set to auto-renew? And what SKU are they signed up for? So we ended up taking those two tables. And with those two tables, we could join them, and we could answer a lot of questions. Who's using the system? Are users seeing failures? Are there certain failures from certain regions that we can reach out to? But as we were running these Spark jobs, for every piece of insight we wanted to get, we were spending 20, 30 minutes, which really limits the value you can get out of your data. So what we ended up doing was having a Spark job that aggregated all of this raw data into daily, hourly, and most recently weekly tables, so the jobs can look at that. And this hourly job, though it is batch right now, we're looking to move it into Spark streaming so we don't have to pay the cost of writing and then reading the data back out. Once we switched to that, using the same schema, we had all the jobs switch to the aggregated data. They then started taking 20 to 30 seconds, so now we can get a lot more value out of the data that we have inside. So what were the results? Well, we were able to answer a lot of those questions. Are users happy with the service they're receiving? Well, you still don't have a good answer for that other than the feedback that we get from customers and being able to see the availability. So we do go reach out to customers, but just from the Cassandra data, we didn't have a concrete answer. Are users fully utilizing the service they're paying for? That we can see. The metadata says how many licenses they have. We can see how many users are using those licenses. And we've been able to reach out to organizations and say, hey, we can work with you to save money. Are users hitting issues we can proactively help them with? We have a whole team in Office 365 that gets the output of this data, the availability of customers, what users are hitting issues, and they're able to reach out to each one of those organizations and say, hey, we see that these users are having problems. Can we go work with your admin and try to fix them? And sometimes it's admin side, sometimes it's our side. And how's the user experience over their lifetime? Well, that's hard to answer since we just started this recently and we've had users for a long time, but we do maintain now long-term data on user availability and how users are using our system. Now, the great feedback we got from support and customers really inspired us to know that we're doing the right thing. Support agents, when you call them, they don't have to go and ask you all these questions. What services are you using? Where are you failing? Now they just look it up and they know, which is fantastic. We've saved customers money. And we found an interesting thing that sometimes credit cards are expired when a user's service is coming to an end. And now we can say, oh, they're still using the service. Let's reach out to them instead of shutting them down. So everything worked perfectly. No problems. But that's not true. So just like everyone else that we were seeing at these talks, bad data modeling was the problem. Huge partitions, 1 to 2 gigabytes. We had no idea what we were doing. And we didn't use date-tiered compaction for date-tiered tables. So we had a lot of compaction overhead going on. Our other biggest issue were not watching metrics. We had too many block flush writers, too many drop mutations. The number of files on the OS was set lower than the number of SS tables that we had, which immediately caused Cassandra to hit an out-of-memory error. And our SS table count got too high, and that's where you really have to work to bring it back down. You have to monitor that closely. So we use Ops Center now for monitoring that. So why did we choose Azure? You're probably thinking, well, they're Microsoft. Of course, they chose Azure. But we really wanted to look at this as a cost-benefit analysis. So we knew that we wanted to use the cloud. We didn't want to manage bare metal. So we had to evaluate what cloud provider did we want to use. And we went and looked at operational costs, because that's more important than the financial costs that you're going to pay, regardless of what cloud provider you use. And we've been using Azure for 5+ years, writing tools around them for deployment and monitoring and managing the service. So that was really the cheapest way for us to go and have our current DevOps team be able to manage the service. We also work closely with Azure support, and we love trying things out on Azure because we can try to break them. And it's always fun to try to break someone in your company. Why Cassandra? I talked a bit about this. The biggest thing for us was didn't enforce full consistency. We can decide what data is important that we get all of it, and what data is it okay if we lose some of it because we're looking at an aggregate. The bad things were we had to run it ourselves. We would have loved a hosted solution, less overhead on the team, but so far it actually hasn't been bad. And then why DataStax? Well, of course, training. They provide integration, so it's easy for us to get Spark and Cassandra working. We have Ops Center, but to me, support. There were so many times in the beginning where I see Chuck taking a picture over there, where we were actually hitting problems and we couldn't figure it out. We didn't know the code base, so we just went to DataStax and we said, please help. And when you have VPs yelling at you saying, hey, this needs to get up, DataStax is there to back you up, which is fantastic. So now I'm going to hand it over to Silvano, who's going to tell you how you can run it yourself.
Yeah, thanks a lot, Sean. And yeah, I'm from Azure Engineering. My name is Silvano Coriani. My team, specifically Azure Customer Advisory team, is helping first-party services like Office 365, like Skype, Dynamics, to give you some examples, but also external customers to onboard on Azure their largest and more complex solutions. And we are talking about end-to-end solutions, including multiple Azure services, and specifically, I'm more focused on the data tier, and that's why I had some experience working with customers that onboarded large Cassandra clusters on top of Azure. So Sean was mentioning hosted services, and we are not there yet, having a full hosted Cassandra service, fully managed, available on Azure. But we do have a number of options for you in order to deploy your own Cassandra topologies on top of the Azure platform. I would divide this into two main buckets. One is what Scott Guthrie actually presented yesterday during the keynote. That is our marketplace-based offering for Cassandra. We worked a lot with DataStax in order to integrate into our marketplace section of the Azure portal a simplified way of deploying your Cassandra clusters, where you essentially can bring your own license and deploy production and non-production clusters based on a number of attributes and configuration options. You can start small with, for example, 4 nodes clusters and go up to 90 nodes. These are, pre-baked options that we have in the user interface whenever you are actually clicking, create a brand new Cassandra cluster on top of Azure. So you can pick up essentially some options like the VM size, the node size, the VM type, and this particular marketplace offering today is limited to a single VNet within a single Azure region. When you are entering all the attributes, basically you get your cluster up and running. You can access the Op Center through that URL that you see on the bottom of this slide, and essentially you can start interacting and managing with your Cassandra cluster. You may add additional services, additional compute nodes or whatever that are actually consuming or interacting with the Cassandra service within that VNet, or you may have a more complex networking topology that actually is part of your overall solution. The other option that we have is actually to let you define your own deployment topology, right? And in general, this goes through a number of options and selections that you have, that you need to have. First of all, you need to decide how you want to group your resources within your larger deployment topologies. If you have a compute tier, if you have a data tier, multiple services interacting with each other, you will need to define how you want to manage those different resources in Azure. And then you want to actually define how your compute and storage resources typically are configured. You need to decide, if you want to leverage, ephemeral disks local to the single compute node, or if you prefer to go to a persistent, durable storage. This is we know this is a kind of a sensitive topic in terms of selecting which one is the best for your particular workload, but we offer both actually, and we will see a little bit later more details on this, and how, for example, to organize your operational activities like backups, taking snapshots of your Cassandra databases and so on. Third, typical area of selection for defining your topology is about networking. Sean mentioned that they consider it in their deployment a single region, a single data center deployment within a single VNet. We have seen other customers actually deploying Cassandra nodes across multiple physical regions, multiple physical data centers, and using VNet to VNet connectivity. And we will see some of the options and some performance considerations around this three-layer compute, network, and storage options that we have available today in Azure. So in terms of organizing resources within your Azure deployments, we recently introduced Azure Resource Manager as the backbone and the provisioning and managing mechanism across all Azure services. This is a recent improvement that we introduced that brings a lot of new capabilities compared to what we used to have in the past. ARM, or as we call it, Azure Resource Manager, is fully RBAC based, so you can define your role-based access control to all resources, all actions, all operations that you are doing across your subscriptions and deployments. Is template-driven, so you can define your templates using a JSON-based dialect, and how all the resources will be deployed in a single fashion through the orchestration engine that is part of the Azure Resource Manager itself. It offers you two models: the declarative model, where you're passing a template to the ARM engine, or the imperative one, where you're actually interacting with resources within resource groups by executing actions and commands against those resources. Is offering some idempotency capabilities so that you can reply your particular deployment options, making sure that you are not duplicating resource deployments, operations, and so on. And is multi-service. You can include infrastructural components, compute, node, networking, storage, but also managed services like, for example, Azure SQL DB as a relational database service, or any other service in the platform. And is multi-region by definition, because you can group logically together resources that are physically deployed in multiple data centers. And this is where, for example, you can start organizing clusters that are effectively deployed in multiple regions. Resource group is a fundamental entity within Azure Resource Manager. Is a logical container, as I said, where each resource needs to belong to. These resource groups are effectively the unit of lifecycle management for your Azure resources. So whenever you are deploying, for example, a Cassandra cluster, you need to define, as an example, your networking topology and your compute nodes topology. You may want to separate these into two different resource groups, and this is giving you the ability to essentially define different lifecycle terms for these different resources deployed. So you may want to, for example, get rid of your compute nodes because you are in a development environment, and keep all the infrastructural components deployed, and deploy, for example, a new configuration on top of that. Deployment is another first-class concept in Azure Resource Manager. Basically, you can organize and track this template execution, deployment template execution. You can read, diagnostic information out of these deployments to understand if everything went well. And you can also create nested deployments if your deployment topology is so complex that requires some form of organization, like, for example, precedences and some more complex processes behind the scenes. So Azure Resource Manager is actually helping us to describe the topology of our solution deployed on Azure. But within each node, of course, we will need to execute a number of configuration operations, and in Azure and in Azure Resource Manager, we have the options to install on each node a set of VM extensions that are basically dedicated for a particular set of tasks. For example, we have third-party extensions like, for example, Chef and Puppet in order to automate configuration of single nodes. We have custom script extensions that can deploy scripts from our own repositories and start doing VM configurations. The marketplace offering that Scott showed today, for example, for each compute node, for each Cassandra cluster node, is injecting, of course, everything from the Java SDK up to the Ops Center for the Ops Center node, and then is automating all the deployment tasks for us. And at the end of the day, is giving us the Cassandra cluster up and running. But these extensions can also help you, for example, in the compute tier, in your application server tier, in order to inject on both Windows and Linux machines whatever application framework your solution is actually requiring. And these ARM templates, we see a lot of end customers, but also ISVs or system integrators that are starting to rely on these templates in order to organize their deployments. These templates may be related to a particular solution area within your bigger infrastructure. For example, building a particular Cassandra cluster, or the templates may describe the entire solution end to end. And by using this nested template mechanism, we give you the ability actually to orchestrate very complex deployment topology within a single process, and by using a single provisioning engine. And as I said, the marketplace offering is based on the same template mechanism that you can use yourself in order to create your highly automated deployment tasks. As a best practice, what we have seen is that most of these templates are organized in order to deploy, to simplify essentially the set of options that you have available for your deployments, grouping these options within some t-shirt sizes type of deployments, right? So that if you need a small cluster, you know that automatically you will get a given configuration in terms of storage, networking, and compute nodes. If you need a medium or large, these configurations will be different. And you can automate these different options within the same template by adopting this nested template mechanism. So based on the parameters that you will pass, different sub-templates or nested templates will be called behind the scenes. So there is a very interesting white paper that is actually describing how you can design these complex topologies for deployment by nesting together and joining together multiple templates and nested templates. This is giving you also the ability, for example, to maintain, to evolve, to test, debug single, smaller units of your deployment process, but orchestrate, the entire units within a single environment. So, but at the end of the day, every ARM template deployment will be based on a set of parameters that you will pass, username, passwords for compute nodes, network configuration, the region where you want to deploy that particular template into, plus a number of other running parameters, and you will have, this nested structure of template that will give you the ability to define, for example, to configure in a different way your Ops Center nodes compared to your the Cassandra nodes in your Cassandra cluster, right? So you will define these roles within your larger deployment, and ARM is giving you the ability to automate both, the resource, deployment, but also resource configuration within each type of different deployment. So if you are interested in this topic, I highly recommend you to go to these two GitHub repos. The first one is maintained by Microsoft and is containing right now more than 200, if I remember correctly, different deployment templates orchestrating large solutions, including a lot of OSS frameworks and applications from Cassandra to Mongo to Elasticsearch and a number of others. And also is also showing step by step, how you can assemble these different capabilities and create larger templates. DataStax, on the other hand, is evolving, their ARM deployment-based templates, and in their own GitHub repo, basically today they are offering the ability to deploy your DataStax cluster in the best optimized way possible. And there are also in the deck a couple of links that can give you the ability to go directly to the training center in DataStax and see, for example, how to deploy with a CLI or with the Azure Marketplace Cassandra on top of Azure. So what kind of, in terms of compute and storage options, these are, of course, super interesting topics in order to achieve your ratio, your sweet spot in terms of performance and scale. Okay, we do recommend a couple of compute families for hosting Cassandra nodes. We do have this series. The series is based on local SSD disks. Is optimized. It has Intel processors, and it's definitely recommended if you want to, for example, balance costs and performance, because it's cheaper than, for example, the G series, that is our top class VM family. But you can still get a lot of performance, for example, from ephemeral node. Even the biggest VM from this series can give you up to 60,000 IOPS and sub-millisecond latency for local disks. But we do also offer the ability to attach remote storage, networked storage. In particular, for production clusters, we recommend premium storage. That is our provisioned IOPS mechanism that is giving you low latency and high throughput capabilities on top of the DS or the GS series of VMs. So you can, for example, stripe together a number of premium storage disks and get up to 80,000 IOPS, and if I remember correctly, for the latest development, up to 2 gigabytes per second in terms of disk throughput for a single node. So you can start small with few cores and local SSD disks, and go up to 32 cores and terabytes of high performance, low latency storage attached to each node. We do also have a standard storage option that is way cheaper, that we typically suggest for example, backup snapshots or these kind of purposes, not for hosting data and commit logs kind of files. It's commit data and commit logs are better suited for the local SSD drive or for the premium storage option in case you want durable storage for hosting your data. In terms of networking deployment options, depending on your network topology strategy, your application factor, and so on and so forth, we do offer, as a basic concept, this idea of VNet. So this is, of course, a private network environment where your nodes can communicate to each other with low latency and high bandwidth. Actually, we don't throttle nodes that are talking to each other within the same VNet, and the only limit is actually the ability of a single VM, essentially the bandwidth available for each VNet, and we can go up to 20 gigabit per second for the largest VM that we have, the G5 or GS5 in terms of VM size. If we want to implement a cross-region deployment, And for example, partition data across physical data centers. We do have VNet to VNet gateways available that are giving you the ability to create a single address space within multiple data centers. Right now, we do have two options in terms of gateway, the standard and the high performance one. The high performance one can give you up to 200 megabit per second in terms of throughput, and of course the latency will depend on how far the two data centers that you are selecting in terms of deploying the different multiple nodes are. We see we do recommend some geo-pairing between regions if you want to maintain low latency, and we don't have a latency SLA. Actually, nobody in the industry have a network SLA in that on this standpoint. But the measures that we took are around 20 millisecond latency between these geo-paired data centers that we have, for example, West US and South Central US, or some of the other 19 or 20, I don't remember exactly the number today, regions that we have around the world. These gateways also have the ability to disable encryption on these VPN tunnels in case you already have application-based encryption, like Cassandra can offer you, and by turning off the encryption, you can get some additional bandwidth just because the CPUs and compute capabilities on these gateway nodes will don't need to actually compute all the encryption part. So we'll give you some more bandwidth between your different VNets across multiple data centers. So just to summarize, in Azure, we do have multiple options to give you the ability to deploy your Cassandra clusters. We do have an highly automated, simplified mode through the marketplace offering, where you just click on, create your new cluster, and the cluster will be deployed in minutes. The last test that I've done is for a 40 node cluster was something like 15 to 20 minutes. And you can get your environment up and running, your ops centers up and running, and you are ready to go and to start developing applications against that. Or you may want to create your own customized deployment through a set of well-organized deployment options that are managed and orchestrated through Azure Resource Manager. So if you want to customize, if you have a very specific set of requirements that you want to customize, Azure Resource Manager is definitely the way to go. And there are a lot of examples and best practices and guidance available to let you understand how you can leverage this technology to deploy your Cassandra cluster.
Okay, so we have about 2.5 minutes left, so we can take questions. Any questions that we don't get here, feel free to tweet or email us.
Large memory machines and G1 garbage collection. Have you tried to push heap size to higher limits? Because you can use up to 100 gigabyte with G1.
So we have only gone as high as 20 gigabytes. And the reason that we didn't go above that was we didn't really need it, but also DataStax had done a bunch of testing, and they found that 20 gigabytes was actually a really good setting on your Spark nodes with G1. So we haven't done anything higher.
And the second question is, have you compared the performance of bare metal Cassandra nodes with the virtual nodes in Azure and cloud?
So my team doesn't have data on bare metal. I don't know if Silvano, if you have any.
Yeah, it really depends on some. To give you an example, the largest VM families and VM size that we have are actually owning the entire physical node. So I'm assuming performance are exactly on par with a similar equipped hardware environment. But depending on your requirements, your VM type and VM size, you can get, of course, different behavior. We think, at the hypervisor level, we are doing a good job in isolating, performance characteristics of different tenants sitting on the same physical host. So there is a good, matching between given VM of that size and an equivalent hardware equipment. Of course, depending on your storage option, if it's a local storage versus remote storage, this can introduce a little bit of variance.
And this might be something DataStax has done some tests on, so we can always talk to them. Okay, looks like there's a question right there.
Yeah, I'm interested in your choice of date-tiered, since that it's kind of fundamentally broken in its implementation. So I was wondering how you've been working with it.
So our table, data comes in, we never update any data. We have hit some date-tiered compaction bugs, such as it needing to scan all the SS tables and that taking a long time and that slowing compaction down. So when we've run into any of those, we've worked with DataStax. The good thing is anytime we've gone to DataStax, they've already gotten that same problem from another customer and they have a patch for us. So they've been really been able to help us through that problem. And so far our compaction overhead has really gone down with date-tiered. Before we were using size tiered, but it looks like we're out of time. So we'll be around after the talk if you want to have ask any questions, and tweet and email us. Thank you.
Thanks a lot.